Okay, everyone, welcome back. We're going to keep talking a little bit about mixed models here. So let me make myself small. And I'll make myself really small and I will hang out down there in the corner. So just to remind ourselves of where we are at, we had these data called yields. And within yields, we had what? Well, we were interested in determining whether or not these different factors, irrigation, density, and fertilizer, somehow influence yield. And what we've been playing with thus far is just a simple model where we're only including irrigation in the model. We're ignoring the fertilizer and the density treatment. But then we also conducted this experiment across 4 fields. And what we decided to do last time was we were going to treat fields as a random or varying effect. Largely because we want to account for the fact that there could be differences among the fields that we don't have any control over, whereas for example, with like irrigation, we have control over that. So we would call that a fixed effect. With field, we can consider it a random effect. We also might want to think of them as being a random effect because the fields themselves are basically 4 draws from a possible population of fields that we could have done the experiment. We just happen to use these 4 different fields. And so we wanted to account for differences that might just be evident across those 4 different fields that have nothing to do with our treatments, but they can certainly affect the variance estimates around our parameters. So we're going to control for that by putting some structure to the error part of our model. And we did that using the Elmer function from the LME4 package. And using this syntax here, this is how we asked R very kindly if it would be so kind as to give each field its own intercept. So we're going to allow the baseline of each field to be different, so that way we can actually go ahead and do the hypothesis testing on our fixed effects while controlling for all of that variation that we don't necessarily care about, but we can certainly model. Since we know that some of that error or residual variation will be explained just simply because there's going to be variation among fields. And so when we finished off, we did this, we ran our model, and we looked at the summary of the model, and I pointed out that there is no p-value associated with these fixed effects. And in fact, if we were to use the ANOVA function, the built-in ANOVA function, we'd see that we get what they're calling an analysis of variance table, but it's not providing us with all of the information that we're used to seeing in a ANOVA table. In particular, we are not getting any information about what's happening in the residual variation. And that's because there's no generally universally accepted way to do hypothesis testing on a mixed model. There's actually a number of different methods, and all of them could be argued that they are fine and they are appropriate, but there's not a single best way to do it. And the authors of R, I'm assuming, didn't want to get into that argument with a bunch of statisticians, so they decided to provide as much information as possible without doing the actual hypothesis testing. And so, but we want to do the hypothesis testing. Right now we have a model where we have irrigation in the model, and we'd like to know whether or not irrigation should be included in that model or not. If it should be included in that model, then that would mean that the irrigation treatment would be significant. And if it weren't significant, that means the best that we could do is just calculate a grand mean. And so I'm going to go over today briefly 3 different ways in which we can do hypothesis testing when dealing with mixed models. 2 of them are pretty similar to one another, and one of them is a little different, but it might be more familiar to you because it actually does put it into an analysis of variance framework. And so why is it that there's no agreement as to how to do the hypothesis testing on a mixed model? And it all comes down to there is no general agreement as to what the appropriate degrees of freedom should be. Because remember, when we do a standard ANOVA, that the degrees of freedom in the denominator are the residual degrees of freedom, and that's the leftover random variables that we have after we calculate, the grand mean and all of our other parameter estimates. Because we've put structure into the error term using maximum likelihood, we don't really have, there is no agreed upon degrees of freedom for the denominator, and hence we have to come up with other ways of thinking about that. So the first way that we can deal with hypothesis testing is to do what's called a likelihood ratio test. And a likelihood ratio test, as the name implies, looks at the ratio of two likelihoods of two models. And then it asks whether or not that ratio is bigger, or if those models are significantly different from one another. And the general setup for a likelihood ratio test, I'll use my fancy whiteboard here, is we would start with the likelihood of what we'll call a null model divided by the likelihood of what we can call the full model, okay? And we'll turn that into log because we like to deal with logs, and then we will multiply that by -2. And what that's going to calculate, that -2, whenever you're multiplying that by a log likelihood, that's creating what's called the deviance of the model. In principle, this should be distributed as, it should be chi-squared distributed. And so if we wanted to compare those two, what we can do is we can take these two models. So here I have the mod full and I have the mod null. Since we're going to be extracting the likelihoods out of that, we can go ahead and say reml equals false. So granted, oh no, I don't want to type it there. Come on, get it together, Jim. Let's see here. What? Killing me. There we go. And so I'm saying reml equals false. That way the entire model itself is based upon the log likelihood. And then I can, or the whole model is based upon a maximum likelihood estimation. So we know that the parameter estimates are going to be biased, but this is the only way that we can extract the true likelihood out of the model, is to do the entire model playing by the same rules using a maximum likelihood approach. And so here I have mod full and mod null. And so again, here's the model, here's the parameter estimates that we saw before for the full model. For the null model, all we have is an estimate for the grand mean. And so here's our two different models. And I want to point out that the null model is actually nested within the full model, right? So it's a nested structure where, if you recall, like when we were using AIC, we could compare all kinds of different models, and they didn't necessarily have to include any of the subset of the same predictors. With a likelihood ratio test, our full model is one that includes all the parameters of interest at that moment, and then our null model is the one that doesn't include those parameters, but it doesn't include any other additional parameters. So whereas in AIC, you could compare, say in this example here, a model that just has irrigation and a model that just has density, you can't do that with a likelihood ratio test. The likelihood ratio test is always going to be something where it's a nested structure of how the models are put together. And so now I have these two models, and as we've played with a little bit before, is that we can extract the log likelihood, log dot like, oh, it's just log like of what? Of our mod full, what, killing me, oh, this has to be capitalized, okay. And so there is the log likelihood of the full model. And then similarly, we can extract the log likelihood of the null model. Okay, so now we have two likelihoods. Our null model is negative, up here would be negative 317.48, and down here would be negative 302.773. So we could look at the ratio between those two, and I will do that. I will copy and I will paste. Here I'm putting this little bracket 1, so it's just extracting that value for the likelihood, so I don't have to deal with those degrees of freedom. So we can go ahead and we can do that, and now we have, that is that ratio. And so now if we were to take that value, -2 times the log of that ratio, we get 29.43083. We could then take that number and we could compare it against a chi-squared distribution. How we determine the appropriate degrees of freedom doing a likelihood ratio test. The appropriate degrees of freedom that we will use for the likelihood for the chi-squared distribution is going to be the difference in the number of free parameters between the two models. And so if we went back here, the full model, it's telling us that we have 4 degrees of freedom. And it's telling us we have 4 degrees of freedom because we've estimated an intercept, we've estimated a slope for the effective irrigation, and then we've also estimated 2 different groups of parameters for the error term. We have one that describes the among fields component, which is our random effect, and then we still have all the leftover variation. And then for our null model, all we've done is the grand mean, and then again our 2 different components of the error structure. The actual values of those degrees of freedom don't matter. What matters is the difference in the degrees of freedom between the 2 models. So in this case here, we would have 1 degree of freedom. So we would go and we would look at the cumulative distribution function for a chi-squared distribution. That would be the value with 1 degree of freedom. Okay. I will point out, just in case it was confusing you, why I put that exp there, and that's because the log-like function extracts the log likelihood, and if I want to use this math here, I don't want the log likelihood, I want the likelihood, so I had to exponentiate those values. This is the exact same thing as if we were to simply take the log likelihoods. So here's the log likelihood for the null model, and then here is the log likelihood for the full model. Recall that when we're in log land, those things that we otherwise would divide, we now subtract. So we'll take the log likelihood of the null model minus the log likelihood of the full model. We'll take that value and we will multiply it by -2. And that is going to give us the same answer as we got when we did it the long way. So this is usually the standard way of doing it, because usually we're extracting the log likelihood because the actual likelihoods end up being super small numbers, and we end up starting to have all those problems that we have with floating point problems and rounding errors in the computer. So we stick with log. Plus it's easier to subtract than it is to divide big giant numbers. Okay, so built into R, we can do this without doing all of that math. Right, without doing this, and we can use that lowercase ANOVA function, and that lowercase ANOVA function, if we were to give it 2 models, we'll give it our null model, and then we're going to give it our full model. What it will do is it will do the likelihood ratio test for us. So I go ahead and I do that, and right here is the chi-squared statistic that we generated up here. Same number is up here, is the same number that R is giving us here. That's good. That means that we're doing the arithmetic correctly. And then again, it's looking at a chi-square distribution with 1 degree of freedom, and the p-value is 5.7 times 10 to the -8th. So if our alpha is 0.05, we feel pretty good saying that irrigation is significant and it should remain in the model. If we had not said REML equals false, just to kind of illustrate something, case. So I'm going to go ahead and do that. Now I have fit both those models using restricted maximum likelihood or residual maximum likelihood, where we're only using the likelihood for the error structure, but we're not using the likelihood for the fixed part of the model. If I then were to compare those models, we will get this announcement from R that it's telling us that it's going to refit those models using ML. So R will do that automatically for you if you're using the lowercase ANOVA function to do a likelihood ratio test comparing 2 models. I point that out because in older books and in older tutorials, you had to have that argument in there saying REML equals false when you were comparing 2 models. But now R does it automatically for you, and it just lets you know that it's refitting those 2 models. And so that is one very valid way that you could do hypothesis testing then on this mixed model. So we would walk away from this and we would say irrigation appears to be important. Chi-squared is 29.43, degrees of freedom is 1, p is less than 0.05, or however, we could say 0.057, whatever. I guess it'd be a lot of zeros than a 5.7. Okay, so that is the likelihood ratio approach. So there's a slightly different variation of the likelihood ratio approach, which is called a Welch chi-squared test. And it is very, very similar to the likelihood ratio, except it also is including a little bit of information criterion in it behind the scenes. I'm not going to even bother showing the math on it. It's not terribly exciting. And at the end of the day, you're still going to get something that you're going to compare against a chi-squared distribution to test for statistical significance. The easy way to do the Welch one is to use that package CAR that we've been using, the one that is very kind and it gives us the marginal sums, p-values and f-ratios based upon the marginal sums of squares. If we were to use that exact same function with an Elmer object, which is the mixed model object, and if we were to put our full model into the ANOVA function, we get an analysis of deviance, type 2 Wald chi-square test. Here is our chi-squared value, and then here are our p-values. Notice that they're not exactly the same between the likelihood ratio and the Wald approach. The Wald approach tends to have a lower p-value because it tends to have a higher chi-squared. There are no real general rules of thumb, frustratingly, as to what the best is. I often use the capital A ANOVA function just because it's convenient, because I don't have to type out the full model and the reduced model and then compare the two using the lowercase ANOVA function. The capital A ANOVA function just seems to be a little bit, it's just more efficient time-wise. There are some people who advocate using the likelihood ratio test when you have relatively small sample sizes. Unfortunately, there's no real rule as to what defines a relatively small sample size. In our example here, we have 20 replicates per field, so I would kind of feel as though it's probably small. But there's no magical cutoff as to what is small and what is big. And like I said, I usually use the capital A ANOVA function. Okay, so those are the two kind of likelihood ratio type approaches that we might consider. Oh, and I'll also say that there would be nothing wrong with is it capital AIC or is it lowercase AIC? Oh, yeah, it is. There would actually be nothing wrong with just using AIC to compare the two models. Here we see that the full model has a lower AIC score, so it's the better model. That's entirely fine, but there's no hypothesis testing involved with that. And if you're going into an analysis where you're going to do null hypothesis testing, you kind of really need that p-value. If you're just interested in comparing the two models and saying what model you think is better, if you want to come up with some kind of prediction or look at the parameter values, you could probably go ahead and use the AIC. Certainly it wouldn't be wrong. Unfortunately, a lot of people in the universe that review scientific literature might not have enough statistical savvy to know that that's actually a totally fine thing to do. So when it comes to hypothesis testing, you can't use AIC, but if you just wanted to compare models, there is nothing wrong with using the AIC. I just wanted to mention that since we are playing around with we're playing around with likelihoods, and AIC is obviously something that we can always extract out of a likelihood. Okay, so the third way in which we can do hypothesis testing will look more familiar to everyone. And what we're going to have to do is we're going to have to load in a new library called Elmer Test. And so I'm going to load in this library called Elmer Test. And I want to point out that it's telling me that it's masking certain things. It's masking the Elmer function from the LME4 package, meaning that there's another function that's called Elmer that's in Elmer Test that will do roughly the same thing, but it's a slightly different type of an object. And then it's also overwriting the step function from the stats, from the base stats package. And, you know, spoiler alert, we're going to use that in the future because that's going to be something that's going to tell us about stepwise model selection. We're going to be able to use that in this mixed modeling framework if we use Elmer test. So I'm kind of a big fan of Elmer test. I just stumbled across it a couple of years ago, and I kind of like how it behaves. But so since we have, I'm going to go back up here and I'm going to cut and paste this. I'm going to have to rerun this model using the Elmer function again, because right now my version of this model was created by the LME4 package, and now when I run it again, now it's being created by the Elmer test package. And you can see that everything pretty much looks the same. The only difference is that here it's saying it's fit by REML using it's an Elmer mod object, whereas here it's an Elmer mod Elmer test object. And it just has slightly different pieces of information that behind the scenes the computer program is using. And so once I've created that, I can now do an ANOVA on the model. And notice now this looks more like our familiar ANOVA table. This looks somewhat familiar. What we have is the hypothesis testing on the effective irrigation. If we look here at the F value and the P, or if we look at the P value, it's very, very similar in orders of magnitude being small to both the likelihood ratio and the Welch likelihood ratio variant of that. But we have an actual p-value that's set up in the framework of an ANOVA table. So we could say, you know, irrigation is an important effect. Numerator degrees of freedom is 1. Denominator degrees of freedom is 67. And there's our F value and there's our P value. And so this is much more similar to the traditional method of doing mixed models. And by traditional method, I mean before we all had pretty fast machines readily available to us in the form of a computer that we would be able to do the hypothesis testing on. Yeah, so let's talk about we can do one more thing. Since we got time, let's think about the old school way of doing things. The old school way of doing things, before we were using REML, or restricted maximum likelihood for the error term, would have been to simply put field in the model. And I will call this old school. And so with that, we could do, still want to do marginal sums of squares. But this is the type of output we would get way back in those days, which is just to put it in there as a fixed effect. I point out that here is identical to what we had when we used the Elmer test function up here. Okay, we're getting the exact same F value and the exact same P value. And that's why I said this is the more traditional method. This deviates slightly from the more traditional method when we start building models that have a much more complex error structure, which we'll get to in our next discussion. Okay. Yeah, and so that's the old way, and we got 3 new ways. Again, using the Elmer test ANOVA function might just make you more comfortable just because it looks like a familiar ANOVA table, and there's nothing wrong with doing that method. Again, most people either use that method or they use either an analysis of deviance or a likelihood ratio test. I figured it was important to mention all 3 of those because they're roughly equally as common in the primary literature. So there isn't any evidence out there yet that there's a one favored method over the other. Okay, so now we know a little bit about doing hypothesis testing on a mixed model. And when we come back in the future, we'll make slightly more complex models and maybe more complex error structures. And then we'll talk a little bit about model selection. And then we should be ready to play around a little bit with mixed models. So on that, stay safe, stay healthy. I'll talk to y'all soon.
Well, surgery? Well, I can't do that. I'm only a dog. Garsh.